spring evening with a lot of pollen. I don't know how you are all doing with your allergies. I'm suffering. So if I'm on low energy today, you can understand. So we are moving on to the next idea, which is kinematic rates. So far, what have we seen? We have seen measures of deformation, which are static measures, measures of deformation such as strain tensors, which are derived from C and B, which themselves are functions of, so C is F transpose times F and B is F transpose. And what is F? The thing that we keep deformation tensor, which is defined as the gradient of spatial coordinate with respect to material coordinate. Yep, thank you. So next step in our study is to understand the time dependence of deformation. I'm not liking this marker, but I don't have an option. Okay. So consider a quantity, any quantity. Let's say for simplicity, we'll have it as a scalar. We'll write it as G with a dash, which denotes the quantity. Let's say temperature. Okay, G with the dash is temperature, but when you represent it in the spatial form versus the material form, it could have different functional forms. That is the algebraic function that describes this quantity could take a different formula when you do it in the spatial versus the uh, uh, spatial versus the material. Okay, so we'll write G with a dash is equal to, we'll use the usual notation G of x comma t, which is the functional form in the spatial coordinate system. And then we'll also write this is G with a tilde of x comma t in the material coordinate system. We'll write G with a tilde of x, which itself is a function of time and time. Substitute x equal to p of x. To be very general about this. So if we are considering this quantity, and if we are next interested in time derivative, let's talk about this time derivative. Now, I've been telling constantly that rates are more important in the context of fluids, where deformation is a continuous phenomenon and it takes place over time until a load is applied. So again, I'm repeating myself, I know. If you apply a load to a solid, you get deformation in response, and depending on what the load is, at some point the deformation will stop, even when the load is still active. And if you remove the load, a part of the deformation may come back, or it may fully come back, depending on whether you are still within the elastic limit or if you have yielded and moved on to the plastic side. For a fluid, suppose you have a blob of a droplet or a beaker of liquid. If you keep applying a shear force, the liquid will keep on flowing until the load is there. And even after you remove the load, until it has some inertia, it will keep flowing. That's why rivers flow, because they have some momentum. They'll keep on flowing until that momentum is still with them. So when we think of a time derivative, we are invariably going to use this in fluid mechanics context. So let's think of this thought experiment. You have a steady flow. Okay, let's say you have a steady flow, and there is a since you are from civil engineering, I'll give a civil engineering type example. We have a boulder, and the flow is basically turning around the boulder and just going along. So it's like a very quietly flowing river. If you stand anywhere in the river, stick a velocity meter, and you record the signal on that probe, you are trying to measure the velocity at one point. Are we together in the story so far? Now, I told you your river is flowing very gently and steadily, which means at any given point, the velocity should not change over time. At that point, the velocity is constant over time. So if I consider velocity, so here is my top view. I have a river, I hit this marker, and I have a boulder here. So the flow is turning around the boulder, and there is no turbulence, there is nothing, it's all perfectly laminar steady flow. So if you stick your probe in here, we'll call this position X. If you measure velocity at this point X as a function of time, this velocity will be steady over time. That's what steady means, right? But if you move on to, say, for example, this is x1 and this point is x2. So at x1, I have a velocity that is steady. And because the flow has to turn around, whatever x1 is, it can't be same as the x2 because the flow has to accelerate around that object. So you will have x2 to be, let's say, higher, but it will be some other value. It won't be the same value, but the common characteristic between them is it is a constant, but some other constant. Okay. So if your attention is just to one point, just to this point or this one, what is the acceleration of the flow if you are just focused on this single point? What is the acceleration? What do you know about acceleration in the most broadest interpretation? Like, what is actually
velocity over time?
change in velocity over time? If you are focusing on a particle that is like a baseball that is flying across the field, you can track the particle and you can record what its velocity and acceleration. But if you are focusing your attention on the fluid or material that is at this point and finding it out to be a constant over time, can we say the acceleration of the fluid at that point is zero? That is, if I calculate the quantity partial V over partial T calculated at x1, that quantity can be zero. This quantity, which we write A, or I won't call it A yet, I'll just say partial V over partial T at a given spatial point, this would be termed as local. Why local? It is local to this point. You can replace this velocity with any other quantity. It can be temperature, it can be force, it can be deformation, it can be strain, whatever. If you are calculating it with respect to time at any given point, this is local. With me so far? Okay. Now, let's think of the other scenario where at a given time, it's all steady, right? So if I drop a parcel or if I drop like a pollen particle at this point, since it's a very steady flow, eventually that pollen will travel along this streamline and end up here, end up here, end up here, and so on and so forth. That's how rivers work. You drop a log, you pick it up downstream, right? They have a fixed path. So if you observe this little particle that you're dropping here and it's traveling from here to here, obviously its velocity is changing, right? Is that particle accelerating? If you focus if you focus just this volume or this point and focus on the fluid that is in that volume, they are not accelerating locally because the velocity is stable. But if you track a single particle over a trajectory, that particle's velocity is changing because of change in curvature or whatever reason. And can we say that that particle is accelerating?
It has some acceleration.
It has some acceleration. So if we write the change, sorry, I have something else here. So the change in with respect to time, not about a single point. Here, this is about a single point. That's what the word local is used to denote. This is the change of a single particle, and we denote material x to denote the coordinate of the particle as it moves from here to there. We give it a special symbol and we call this the material, the material derivative, as opposed to this being the local derivative. Okay. I really need to go get another marker because this is just driving me insane. Give me 1 minute. Okay, thank you. My apologies. So this derivative with respect to time at a given position or spatial location is called the local derivative. And this one with respect to time, but it does not include just time, it also includes that differentiation with respect to position, and that is called the material derivative. So just like we have been seeing two frames of reference to describe the same quantity, we are now bifurcating into two ways of taking a derivative on these quantities, either locally or as a function of the particle material. Okay. All right. Any thoughts? Anything you want to add to this? So we want to write The time derivative can be bifurcated into two types. The derivative of g tilde with respect to time for a given particle, that would be called the material derivative. That would be the material derivative. And then the material derivative. The local derivative is partial g with respect to t of x comma t evaluated at a given position. So it's the same quantity. Don't think there are like two quantities at work here. It's the same temperature or velocity or whatever you are interested. It's just two ways of describing it. Okay. What is the most basic attribute of a particle, of a continuum particle? Would you say what is a particle? A collection of atoms which we designate as a single particle, and we denote it with using its position or the positions occupied by all the constituents. You call it the particle, and this position is the defining attribute of the particle. Think about that country example I gave. You can take any country. Let's say USA. What is USA? Any territory that is part of America is called USA. Or any atom that is part of that particle, it comes within this vector x, which we use to denote the particle. Okay. So when we start writing this, so we wrote g with a dash, the physical quantity is expressed as g of x comma t, or g with a tilde of x of t. A little confusing here. Just write g of x comma t. And then if we want the rate of change of g, the rate of change of g, what we are saying here is there are two ways to calculate g dot the rate of change of the quantity g with respect to time. What are the two ways? You can look at a single position in space and compute the local derivative. That would be partial g of x comma t with respect to time at x, and it can also be calculated as partial with respect to g tilde of x comma t with respect to time for a given particle. We give a special symbol to this. We start writing it dg over dt to distinguish it from the other one, which is written as a partial derivative. So this is called the local rate of change, otherwise known as derivative, and this is the material derivative. This is the summary of what we have seen so far. Good. Remember what is G? What is this G? What can be choices for G? G could be any physical quantity that you represent, starting with position, velocity, acceleration, temperature, deformation, strain, can be any quantity. Okay. So we'll start with the simplest of choices. We'll start with let G with a bar be the position. When I say position, I could be referring to the x, which is the spatial coordinate. I'm sorry, which is the coordinate in the spatial frame, or I could be referring to the material part. Okay. Now let's come back to that baseball example. You are watching the game, you are seeing the ball flying over the park. How will you calculate the velocity of this particle denoted as x? How is velocity literally calculated? Watch baseball.
Not really, but I've watched before.
I mean, if you watch it on TV, they show you the trajectory and then they kind of do an analysis of where the ball will land, even calculate at what speed the pitcher threw it,
Right.
and where the batter hit it. And same applies for cricket. I know many of you might be following. They tell you exactly what is the speed in which a ball was bowled and how long or where, how far the ball went when it was hit out of the park. So, simple question. If you are the person calculating the velocity of that ball, how do you literally do it? Think and tell me.
Probably with the camera changing, looking at the change in position in the camera frame over time.
From between frame to frame, how much has the position changed between the time between the frames? So if I want to say velocity of the particle, that would be the rate of change of position with respect to time. Velocity is rate of change of position with respect to time, and in which frame is this the correct velocity? Is this in the material frame or in the spatial frame? So we are calculating the rate of change of position with respect to time. It represents what? What does it represent? The velocity of a particle. So this actually is v vector, velocity vector, but with the tilde. This is the velocity of a particle. That's why I wrote velocity of the particle. Just forget the baseball or cricket analogy. And when you bring it back to continuum mechanics, if you have a material particle, it's basically imagined as a lump of matter. The rate at which that particle is changing over time, its position, that is literally the velocity. So this is partial derivative of x for a constant x, which is given as the velocity. I would like you to process that and tell me if that makes sense to you. If not, let's talk a little. I want you to think about it for a minute. What is x? X is phi of x comma t. If I take x derivative with respect to time, that is essentially partial derivative of phi with respect to time at a given x. Okay. So when we say velocity of a particle, it is calculated as the derivative of its spatial coordinate with respect to time. If you know the deformation mapping, you can replace this x with the material x and do the arithmetic or do the derivative calculation. I want one of you or few of you to explain this back to the class so that I understand this is getting across. Is this making sense, or am I just giving you information that you are not accepting?
When you're talking about we see uh, the change in the location of the particle.
Right.
But when we are talking about the spatial coordinate, we can take, for example, the frame and see how the particle is changing the position.
Right.
And I think this is because that's why for the velocity for the material, we use the spatial fluid reasons.
Right. That's correct. The other thing I want to add to that is, in the baseball example, your particle is a ball, which is a rigid body. It's not going to change its shape, it's not going to disintegrate, or it's not going to go into pieces. When you're thinking of a blob of fluid, or even a blob of solid material, when you apply some load on it and squeeze it in some way, it's not going to stay in that same shape. When you say, when you take a baseball and you designate this volume occupied by the ball, let's say the center, you denote the position using X. And with respect to this position, you can define every atom in that ball using some kind of a spatial relationship. And what is a rigid body? A rigid body is one in which the spatial orientation does not change over time. It stays rigid. That's what rigid means, right? Suppose this were not a baseball, you're thinking of a blob of fluid or material that is being squeezed. Over time, this can, let's say, flatten something like this. It can still be at X, or I'll call it X1, or it could be at X2 or whatever. But what is the relationship between this point and the remaining points? That is the shape of the particle. Okay, so when I write X, what is X? What is X denoting? It is denoting where all the particle exists. It's basically the points that are within this shape. Okay, it's very simple for a rigid body to calculate this quantity because you don't have to do it for every little dot in that rigid body. You just have to do it for one point, the center of mass. But if you have a blob of material which is changing shape as well as moving across in space, this X is denoted by, this particle is denoted by the positions of all these particles, all these atoms. And when the deformation happens, you are not going to get the same particles, you are going to get X. Let's say this is X naught. This is X1, and this is X2. X2 is a different set of vectors or positions which denote that particle's instantaneous shape. So what carries over from my baseball analogy is you can take the position and take its derivative for a fixed particle. A rigid body is easy to be fixed, but in our case, in the most general deformation case, keeping this X fixed means what? For a constant X means what? First of all, do you recognize that X can change because of deformation? You squeeze your droplet, it flattens like a pancake or something. It can change. The extent of what constitutes X can change. Okay. So if I ask you for the derivative of position change with respect to time, at a for a constant particle, what does this statement literally mean or translate in English?
Does the constant X means that it stays in the same general shape?
It means it stays in the same shape. If X changes, the only way that could change if shape changes, or in other words, that particle is deformed. It's taking a snapshot of the change in position for a fixed shape of the particle. Of course, in a real particle, if you take a little the droplet of oil that you put in water, it could simultaneously be moving as well as breaking up into smaller droplets or deforming in shape and so on. In reality, this happens concurrently, not one after the other. The mathematics is calculated as the derivative of a function at a given x is equal to the particle velocity. This is the velocity. This is the velocity in the material frame. Material frame. So we started with g being x. If we are interested in g dot, the rate of change of position, the rate of change of position at constant x gives you the particle velocity. Okay. Then what does you take in the same example about baseball curling across the field? You are doing the trajectory analysis. You are taking the rate of change of position, calling it the velocity of the particle. What would you call the rate of change of the second derivative of position for a constant particle? What would this quantity be?
Acceleration.
This would be the acceleration A with a tilde to denote this is the acceleration in the material frame, or we'll call it material acceleration. So what are these two? Both are local derivatives of x of g with a dash which we took as x. With me so far? I hope we didn't overload anything. We just took the most simplest quantity, the spatial position, and found out that the first derivative and second derivative give respectively the particle velocity and particle acceleration, or material velocity and material acceleration. Okay. We'll do the same exercise for this guy, the material x. What happens when you consider materials? So when we write vi. Yeah, they are just considering. So if you consider v to be a vector, v of x comma t, you can write this vi ei cap, right? Because we are using the spatial coordinate, we should just write as component multiplied by the basis in the spatial system. Okay, so if we just take vi, vi itself is a function of x and t. So that we are dealing with a scalar, not with a vector. So we are just dealing with vi, and you can also write vi is equivalent to vi with a tilde. What is x? X is a function of x comma t comma t. I want you to interpret this statement for me. I went from x to material x, but again saying material x is a function of position and time. Please interpret this statement for me. What is uppercase x? Material coordinate. It basically is the coordinate of the particle. And what is a particle? It is a collection of atoms. And each atom at any given time has a position, which is this x. So this x is defined by what all constitutes particle and where and what positions do they occupy. It's not, it's different from this x. I mean, okay, it's not exactly different, but the distinction is instead of referring to the space, they refer to the position occupied by the material particle, and that's why we call it uppercase x or material vector. Okay, so we want to write ai of x comma t is equivalently written as ai tilde of x comma t and time. So previously we saw g dot or the derivative with respect to the spatial coordinates. That's what the local derivative we saw here. If we consider g dot to be equal to the material derivative, what is material derivative? This is partial derivative of g with respect to time at a given position and partial derivative of g with respect to position multiplied by dx dt. Why am I allowed to write this? There's a dot product here. Actually, they want to keep this. Yeah, there is a dot product. That's good. Okay, why am I allowed to write it this way? First of all, what is this quantity? This is dg over dt at constant x. Why am I allowed to expand this as the sum of a time derivative plus the sum of a spatial derivative multiplied by a rate of change of space? We can think of two explanations. I'll first give the mathematical explanation. Suppose you have a function, just old school calculus, you have a function, let's say g equal to g of x comma t. Okay. What is the total rate of change of g with respect to time? That would be partial g with respect to partial t at a given x plus partial g with respect to partial x multiplied by the rate of change of x with respect to time. If x is not a function of time, this term is zero. If x and t are completely independent of each other, what you get as the total derivative is just the partial derivative. But if x and t, if x itself is a function of time as well, then your g is changing with respect to x, but x is also changing with respect to time. This is the old school calculus explanation why when we write x, which we know is a function of position, when you say x is constant, material x is constant, that by extension doesn't mean the spatial x is constant. So you have to allow for the spatial x to change or allow for the spatial x to influence g. That is the mathematical explanation. What is the physical explanation? And a hint I'll give you is think of the example I gave of a steady river flowing around a boulder where the velocity changes from point to point but doesn't change at any given point. Suppose we will make that river a little more turbulent. At any given point, the velocity is also fluctuating. But if you move from, I don't know how many of you know US geography. Memphis is famously on the banks of Mississippi, right? And Mississippi not only flows here, it comes all the way from Minnesota, it comes through St. Louis, and it comes here. I happen to have the pleasure of seeing the Mississippi in Minneapolis as well as living here in Memphis. Minneapolis is where I did my PhD. So you can take, if you want to calculate what is the rate of change of velocity or acceleration of the fluid, hypothetically speaking, in Minneapolis and in Memphis. Of course, the distance is huge. I'm not crazy to think that, but I'm just thinking of two, one upstream location and one downstream location. What is the acceleration of the fluid as it goes from point A to B? The change in position with respect to time. That is, you are here at Minneapolis, which is upstream. Your velocity is changing with respect to time. So you add a component that is the time variation. But as you go from point A to point B, there is a finite rate at which that fluid goes. How fast does the fluid go? Well, it goes as fast as the velocity. That's what velocity is, right? So the quantity that you're trying to calculate, if it is g, which could be temperature or velocity or whatever it is always influenced by the velocity of transport, which is v. For the special case that g is just velocity itself, you get a term which is derivative of v with respect to x and multiplied by dx dt, which is again v. Okay, so here we can write partial g with respect to partial t at a given position plus partial g over partial xj multiplied by partial xj over partial t at given, yeah, and this quantity would be regardless of what g is, this quantity is vj of x comma t. So what is the learning here? The local change in position gets you particle velocity. The local change in velocity or local change in particle velocity gets you particle acceleration. If you consider material derivative, it is influenced by the local change and it is also influenced by the velocity of with which the spatially, I'm sorry, It's influenced by also the spatial change in velocity. For any quantity, this is G. I haven't even told you what G is. This is true for any quantity. Okay. So the important result that we want to write from here is this one right here. G dot for the material derivative involves, this is a dot product I told you, right? So this is basically like writing partial G over partial T plus partial G with respect to xj multiplied by Vj. So you are going to calculate the material derivative for a lot of quantities. Whenever we say material derivative, it has a time dependent term or the local term, and it has an advective term which depends on position. And the reason we call it advective is because advection means the rate at which you move from point. So the rate at which you move from point to point is Bj, and the rate at which that quantity is changing spatially is this partial G over partial x. Okay. In solid mechanics, you very rarely encounter this material derivative in this form because Vj will always be 0 or nearly 0. You are not going to have a bar that is put in a testing machine and you apply a load. It's going to deform, but it's not going to deform to an extent that the material that was at the top is pushed all the way to the bottom. It's not going to deform at that pace. If it is deforming at that rate, it would have already fluidized. It would have already started behaving like a fluid. So here's the question that one of my in a course that I took, the instructor asked: is rock a solid or a fluid? Depends on what? Sorry. So it's like saying it's not only time, it is actually strain rate. If you think of a rock, it looks like a solid. Or what she's saying is over the time scale of 1 hour or 1 day or even one lifetime for us, it looks like a solid. But if you look at it in millions of years or billions of years, that rock would have been subject to shear forces or some kind of geological forces, which slowly, ever so slowly change its shape. That if you take a time lapse video over the time scale of like 100 million years, it will look like it initially was like a block, and over time it became like a rhombus or something. That's what she's saying. It is also a function of the strain rate, in the sense, if you take that rock and if you accelerate it to 100 kilometers per second, and who can do that kind of speeds? Only gravity can accelerate to 100 kilometers per second. And what is the name of a rock that is flying at 100 kilometers per second towards us? That's called either a meteorite or a missile. I mean, missile is anthropogenic, but we'll call it meteor. A meteorite, when it crashes onto a planet or a moon or asteroid, the entire kinetic energy of that whole object is converted, is decelerated to 0 in a snapshot of a second, like 1 second. All that energy is brought to, all the velocity is brought to 0. Guess where that kinetic energy is going? It's going into heating up that boulder so intensely, so quickly, that in a second or less than a second, that boulder turns into a fluid. And then the fluid is basically the droplet. It's like a molten droplet that is interacting with the surface. And then you have deformation or whatever shape change and so on. So it is always a misnomer to say something is a solid or a liquid without specifying either time scale, and I would also add strain rate. What velocity are you dealing with here? If you take a bullet, and do you think a bullet by itself could harm anyone? Even if you throw it really hard, it's how a gun launches, how all that kinetic energy is then abruptly converted into compressive strain, and that goes into applying a load on the surface, whichever that surface is, and that surface most often will not be able to bear that load or absorb that energy. It's going to yield, which is what we call as a bullet hole. Okay, so no material has a strict universal behavior as a solid or a fluid. It's always contextual. Okay, so that is why even if you are a solid mechanics person, you have to learn this stuff because you never know when you will encounter high strain rate deformation. It could be ballistics, it could be Hopkinson bar testing, it could be impact testing, it could be high speed machines. You never know when you will need these tools. Okay, just a little digression. All right, so this is material derivative. So what I'm going to do, we wrote the expression for material derivative of G, right? Now we are going to choose G. So in this expression, we are going to choose G is equal to Vi of x comma t. Vi of x comma t. So we are going to get Vi over dt is equal to partial Vi of x comma t over t for a given particle, which is the partial derivative of Vi with respect to time plus the partial derivative of Vi with respect to time multiplied by partial derivative of xi with respect to time, which is nothing but Vi itself. So this is partial derivative of Vi with respect to time plus Vi, Vi multiplied by partial derivative of Vi with respect to I want to use xj, make sure that we don't this partial derivative of Vi with respect to xj multiplied by xj with respect to time. So this is partial derivative of Vi with respect to time plus Vi with respect to xj multiplied by Vj. So this quantity is Ai of x comma t, the spatial acceleration. What is spatial acceleration? In my river example, if I am sitting outside the experiment, which obviously I am, all I'm interested is if I go from point 1 or if I take any one point, what is the acceleration of the fluid, not just due to the local, but also due to the advection term. That is the spatial acceleration. So if I write Ai is this, and if I multiply by Ei cap on both sides, Vj I'm starting to go towards a vector A, the spatial acceleration vector, equal to partial V over partial T plus, I'm going to call this velocity gradient dot velocity. This quantity here is the derivative of velocity with respect to space. I'm calling it velocity gradient. Velocity gradient. So we give it a symbol and we write A is equal to partial V over partial T plus L dot V. So I strongly suggest that you read section 3.6.1 because everything that I told here is based on a reading of that section. All my example about the velocity meter, you can find it there, but I contextualized it with the river example, but the concept is there. So I'll give a minute. Think about this. And if you have your text, please look at example 3.9. We'll do that.
Pages.
895. So for the second exam, I'm thinking about asking you to access any textbook or notes, but no laptop, cell phone. That'd be okay because although I don't have evidence to make any investigation, but I have some reason to believe people may be using their devices to ask chat GPT, or they may be sending an email or chat message to anybody here or outside to get answers. I'm suspecting that may happen or could have happened. So we'll just do no electronic media. Bring the thickest book that you can find and do the exam. How about that? Okay. I'm not accusing anyone, but that possibility exists. Let's not let it be there. Okay, so please make sure you have access to the textbook. I have 2 copies, which I'm happy to lend for the exam. Okay. All right, problem or example 3.9. Consider the motion x1 is 1 plus t times x1. x2 is 1 plus t whole squared x2, and x3 is 1 plus t squared x3. If a relation between spatial and material x is given, you are now used to the idea of computing the deformation gradient. That is easy, right? F is equal to gradient of x with respect to x in the material. You're used to doing that, right? We just introduced a quantity L, which is gradient of V, or this is partial V over partial X. What is F? A mixed second order tensor with the basis vector taken each from spatial and material coordinate. What about L? Velocity gradient.
Taken over spatial.
So it is a second order tensor in the spatial field.
Frame.
It's a spatial tensor of second order. It's not mixed. That's what I want to say. All right, so we are given this deformation. We want to compute velocity and acceleration. First, let's go for material description. What is the velocity in the material description? That is equal to the rate of change of position with respect to time at a fixed particle. We saw these formulas. I'm just giving you practice of using them. Okay. So you already know what is x as a function of time and constant material position. So you have to treat x1, x2, x3 like they are constants. So you can write this is equal to, if I write it as a vector, this would be x1, this would be 2 times 1 plus t times x2, and this would be 2t x3. Would you agree? So this is the material velocity. This is the velocity of a particle as a function of its material coordinate. If I ask for express the material velocity v with a tilde as a function of x and t, what will you do? You have to eliminate material coordinate from this expression using the original relation. In this case, it's very easy to invert. This is like saying x1 is equal to x1 divided by 1 plus time, x2 is equal to x2 divided by 1 plus time squared, and x3 is equal to x3 divided by 1 plus t squared. So replace x1, x2, x3 with these quantities. So x1 divided by 1 plus time, 2 x2 divided by 1 plus time, and 2t x3 divided by 1 plus t squared. You need to get comfortable in expressing a material quantity in both material coordinates as well as spatial coordinates. With me so far? We have computed velocity. Let's compute acceleration. Again, acceleration in the material description. That would be the second derivative. Acceleration in the material description would be the second derivative of position with respect to time for a fixed particle. That would be, what is the derivative of x1?
Function.
0, 2, x2,
X.
and 2x3. If you look at it in the material coordinates, it looks like something that doesn't change with time, only with the position of the material particle. But the material particle itself changes with position and time. That's the inverse mapping. So it can be a little dizzying with all these forward and backward mappings. But if you keep this relationship clear, that is, if you start with either this or this, rest of it is just being methodical. So I know in the exam I allow like you to bring the book or whatever. I would still advise you to prepare a formula sheet. Keep one sheet, which will be more efficient than looking through the entire book. And by now you can see all the formulas or the tensors that come up. It's easy to prepare that sheet. Okay. All right. So that is material velocity and material acceleration. Now compute the spatial velocity and spatial acceleration. That is, spatial velocity is so this quantity here is also the spatial quantity because it has only the spatial coordinates and time. So all you have to do to go from material to spatial is to use the inverse mapping and get rid of the spatial coordinates. Okay. Will be V of x comma t is V tilde of x, which is then expressed as a function of x and t and time, which would make this x1 over 1 plus t, 2x2 over 1 plus t, and 2tx3 over 1 plus t squared. So what is derivative of v with respect to time? That would be minus v. Let's do this component by component. So ai or a1 of x comma t is partial derivative of v1 with respect to x comma t plus, how do you write this in index notation? L dot v. would be, if this is I instead of 1, this would be Lij Vj. Remember what is L? L is velocity gradient, which is partial V over partial X. So Lij is partial Vi over partial Xj. Okay, so what is if I write A1, I say I equal to 1, A1 of x comma t is, what is B1?
X1 by 1 plus t.
X, the derivative of that would be minus x1 divided by 1 plus t squared. And then for clarity, I'm going to write this is partial V1 over partial x1 multiplied by V1, or I'll write J and J. This is minus x1 divided by 1 plus t squared plus what is V1 over x1? V1 over x1 is non-zero. What is V1 over x2? This V1, V2, V3, V1 depends only on x1. So this is like writing plus
1 by
1 over 1 plus t multiplied by whatever V1 is, which is x1
by
over 1 plus t. And this turns out to be 0. So A1 is 0. What about A2? A2 of x comma t is partial derivative of V2 with respect to time, which is minus 2x2
by 1
1 plus t squared plus
1 plus
1 second partial V2 over xj multiplied by Vj. This is minus 2x2 1 plus t squared plus, what is partial derivative of V2 with respect to xj?
2 by 1 plus t.
V2 with respect to x1 is 0. V2 with respect to x2 alone will be 2 over 1 plus t multiplied by V2 itself, which is
2 by
2x2 divided by
1 plus
1 plus t. Turns out this is also 0. Oh, no, it's not 0. This is 2 times x2 over 1 plus t whole squared, which is not particularly anything. Or if you want to call it, this is like V2 divided by 1 plus t, but that's not necessary. And then what is A3? A3 of x comma t equal to derivative of V3 with respect to time. This is derivative of V3 with respect to time plus partial derivative of V3 with respect to xj multiplied by Vj. So what is the time derivative of this quantity? So that would be 1 plus t squared times 1
minus
minus 2t
t
squared divided by 1 plus t squared, the whole thing multiplied by 2. And then second term, V3 with respect to x1 and x2 are 0. And then you have plus 2t divided by 1 plus t squared And then I have to multiply by V3 as well, which is another 2t divided by 1 plus p squared times x3. Wait, I left out the x3 here. Will this at least cancel? So you have 1 minus t squared plus 4t squared. Sorry, no. 2 minus 4t squared plus 4t squared. So the 2 stays. So this is like writing 2x3 divided by 1 plus t squared whole squared. It's messy, but the point is how to learn to do this calculation. There are four quantities: material velocity, material acceleration, which is just the first and second derivative of the position. Then there is spatial velocity, which is basically obtained by taking the material velocity and transforming it back to spatial coordinates. And then the spatial acceleration, which is got as the material derivative of the spatial velocity. That's a mouthful, but I guess that captures it. So this is a good point to stop, but if you go to the homework, you look at problems 3.15, 3.16, 3.18, 3.19. I don't remember if they are in the homework, but they are still within this discussion of calculating the accelerations and velocities. Okay, 3.15 to 19. Okay. So next lecture we'll continue on to section 3.6.2 and so on. Reminders, exam when?
April 10th.
April 10th. Homework 2 submission 1 week before, April 3rd. Programming assignment
Same.
same day or April 8th. You can take up to April 8th. Okay. I'll hand out your graded exams next week or Tuesday. I've finished grading it. The scores are all posted. I just want to sleep on it before I hand it back. Okay. And I strongly encourage you to come talk to me, discuss your performance, and we can, go over any help you need. Yeah. So I expect to take maybe one more lecture to complete this. I've been saying this, but hopefully only one more lecture. And after that, I want to continue with the third unit, even though that is not not going to be on the exam. Okay. Yeah, we'll meet on Tuesday. Thank you.